All right, let's jump right into this explainer and really master the absolute core of scalable test benches, the UVM agent. You know, if you're in the semiconductor world verifying complex SoCs, you already know verification is, well, it's a beast. So today, we're going to break down the architectural hero that actually brings some order to all that chaos. To kick things off, we've got to address the elephant in the room. That massive industry problem of tangled, totally custom test benches, and why we so desperately need a plug-and-play solution. Because before standardized methodologies came along, every company, sometimes literally every team within a company, just built their own custom frameworks. And honestly, that meant a ton of frustrating, wasted engineering hours, duplicated work, and absolutely zero verification IP reused. You just couldn't easily port your PCIe or ACI verification logic from one project over to the next. That's exactly why the UVM standard, and specifically the UVM agent, was created, to stop us from constantly reinventing the wheel.
So here's our roadmap for today. We're going to cover 1. The UVM agent foundation, 2. Unpacking the architecture, 3. Active versus passive agents, and finally, number 4, the real power of reusable VIP. Let's get into it.
All right, Section 1, the UVM Agent Foundation. Let's clearly define what this architectural hero actually is.
The crucial takeaway here is that the UVM agent acts basically like a standardized adapter. It completely shields the rest of your test bench from the messy, protocol-specific details of your design under test, or DUT. You can really think of the agent as a highly specialized wrapper. Say your chip has interfaces for PCI, Ethernet, and ASIC. Well, you're going to have a separate, dedicated UVM agent for every single one of those protocols. It essentially encapsulates everything you could possibly need to interact with that specific interface.
Now, if we look at the actual object-oriented code, we can see exactly how the agent inherits directly from the UVM_component base class. And because it's a structural component, it acts as a quasi-static entity. What that means is, once it's instantiated during the UVM build phase, it just stays there. It exists throughout the entire duration of your simulation, locked firmly into your verification topology.
Moving on to Section 2, Unpacking the Architecture. Now that we have the foundation set, let's pull this agent apart and see how it works under the hood.
Internally, this whole architecture is built on what we call the agent triad. It's basically 3 distinct components that chunk the workload into really specific roles that play perfectly together. Now, while an agent's build function could theoretically define any topology, a standard active agent universally contains these 3 subcomponents: the sequencer, the driver, and the monitor. They each have a strictly restricted role, which is exactly what keeps the architecture so brilliantly modular.
First up in our triad is the sequencer. This guy serves as the strict arbiter managing the flow of high-level transaction items generated by your sequences. You see, your test scenarios describe abstract behaviors, things like send 10 randomized read requests, but it's the sequencer that actually controls the routing of those abstract sequence items. It acts just like a traffic cop, especially when you have multiple sequences all competing to execute stimulus at the exact same time.
Next up, we have the driver. This is the active actor that pulls those transactions and does the heavy lifting of translating them into raw physical signal transitions right on the hardware interface. Since sequence items are super abstract, like they might literally just say read address X, the driver is the one that has to know all the exact exotic encodings, the timings, and the protocol rules to properly wiggle the bits at the input pins of the DUT. And to do this, it uses a transaction-level modeling, or TLM port, to pull these items securely straight from the sequencer.
And rounding out the triad is the monitor. Now, this is a strictly passive observer that just watches the pins and neatly packages all that activity back into abstract objects for your scoreboards to analyze. The key here? It never, ever drives signals. It only samples them. Once it reconstructs those physical pinwivels back into a clean transaction object, it broadcasts that object out via an analysis port to the other components, like your coverage collectors or scoreboards. So if we follow a single data packet's journey, we can see exactly how this communication flow operates seamlessly down to the pins and right back up again. The sequencer pushes an abstract item, right? Then the sequencer arbitrates and passes it to the driver. The driver translates it and hits the DUT. Almost immediately, the passive monitor sees that physical activity, translates it back up to the transaction level, and sends it out to the rest of the test bench. It's just a perfect continuous loop of stimulus and observation.
All right, Section 3, Active versus Passive Agents. This is super critical because, well, not every agent actually needs to drive stimulus.
Here's the stark contrast. While an active agent is out there busy doing all the driving, a passive agent is strictly a spectator.
It strips away the driver and the sequencer entirely. If you only need to look at port values on an interface without actually injecting any data yourself, the passive agent is 100% your go-to configuration.
And looking at the exact SystemVerilog implementation, this is handled beautifully by the get_is_active function, which dictates which configuration the agent should take on. You usually set this up via an integer parameter right in the configuration database. Depending on whether it returns UVM active or UVM passive, the agent's build phase dynamically decides, okay, do I instantiate the driver and sequencer, or do I just spin up the monitor?
Now you might be wondering, why does this matter so much? Well, when you scale up from block-level testing to full system-level testing, you absolutely need passive agents to observe internal compliance without accidentally overriding live signals. At the block level, sure, you use an active agent to drive a standalone IP block. But when you integrate that block into a massive SoC, that interface is now physically wired to another block inside the chip. You can't actively drive it from the test bench anymore without causing a massive collision. But you still need to monitor it to make sure the protocol is behaving, right? So you literally just flip a configuration switch, the agent becomes passive, and boom, your verification logic scales perfectly.
Let's move into our final section, Section 4, the power of reusable VIP. Let's look at the ultimate payoff for setting all this up.
By intentionally keeping the functional checking separate inside a scoreboard, the UVM agent remains this pure, fully reusable verification IP that you can just drop into literally any future project using the same protocol. Think about it. If you shoved a checking mechanism directly inside your agent or your driver, you'd completely ruin its modularity. Scoreboards are highly specific to your design, like an AES or RAM scoreboard. But an AXI agent, that should really only know how to speak AXI. This strict decoupling is exactly what lets you build a massive library of generic plug-and-play components.
And as industry experts point out, standardizing with UVM drastically improves interoperability. It slashes the cost of reusing IPs with new projects, and it makes it so much easier to port components from block level straight to system level. When you leverage UVM, you aren't just writing a throwaway test bench for today's chip. You're actually building a robust arsenal of standardized, protocol-compliant verification components that you, and honestly, your entire organization, can use on every single chip you design in the future.
So I want to leave you with this final thought to really challenge how you approach your next verification project. Your design is inevitably going to change. Will your test bench survive the update? The core principles of the UVM agent, strict encapsulation, standard communication through TLM ports, and those dynamic active and passive modes, they ensure your test bench doesn't just survive an update, it scales effortlessly right alongside your design. Start leveraging these concepts, build your verification IP modularly, and for goodness sake, stop reinventing the wheel. Thanks for hanging out and learning with me today.